My name is Qiao. I am a professor in the School of Aeronautics and Astronautics at Purdue. I also hold a courtesy appointment in mechanical engineering. I received my PhD in aerospace engineering from the University of Michigan in 2007, and then since then I am a faculty member at Purdue. My research interests are in the areas of fuels, combustion, and propulsion. It's very exciting that right now to be doing chemical propulsion research. There are many new concepts and new technologies. For example, the reusable rockets concept is being developed by SpaceX. If that's successful, that's going to make space travel a lot more affordable. And the other example is hypersonics. The X-51 Wave Rider is designed to ride on its own waves, and then the main component of that system is a supersonic combustion scramjet engine burning JP7 jet fuel. So my lab studies fuels and propellants in chemical reacting flows with applications in energy, defense, space exploration, transportation, and fire safety. Particularly in the past couple of years, we have looked into 4 areas. The first one is high energy density fuels and propellants for high-speed propulsion systems. And the second area is ignition, advanced ignition methods such as plasma-assisted ignition and pre-chamber jet ignition for high-speed flows or for very lean combustion systems. And the third area was the thermodynamics of non-ideal gases for high-pressure flows. And the last area is combustion at small scales for a number of different applications. One of the areas that we've been working on is alternative fuels. As you know, alternative fuels is emerging in the market. So it's important for us to understand the physical property, the chemistry, and the combustion characteristics of these new fuels. So we have developed a setup over here. As you can see, we have a spherical combustion bomb in-house inside the oven. So we have used this facility to test various alternative fuels, and for example, we have measured flame speed of different fuels at varying temperature and pressures, and these data are important in the sense that they can be used to validate the chemical kinetics of these fuels, which is an input for large-scale computational CFD simulations of chemical reacting flows in practical engines. We have also used this facility to study the fire safety of alternative fuels. We have worked with Federal Aviation Agency to look into several fuels that FAA have just certified in terms of their fire safety characteristics. For example, the minimum ignition energy, flammability limits, pool fire spray rates, and fire suppression. So the result can help FAA to determine whether they need to change their protocols or procedures in terms of firefighting in aircraft engines and also in airport. High-speed propulsion systems require high-performance fuels. For example, we want high energy density, fast and tunable ignition, and fast burning rate. So we have been studying novel concepts such as nanofluid fuels, and then the idea was to suspend energetic or catalyst nanoparticles in liquid fuels to enhance the energy density and to promote ignition. So we have looked into these fields and found very interesting physical and chemical and combustion characteristics of these fuels. Most recently, we also explored a new concept, which is to use highly conductive carbon-based nanostructures as additives to enhance the performance of solid propellant. We have demonstrated for the first time, for example, using graphene foam, the burn rate of the propellant can be enhanced 5 to 6 times. And we believe this is because of the unique structure of graphene foam, the 3D, porous, highly connected, which promote heat transport. And most recently, we extended that concept one step further using graphene foam doped with catalyst for solid propellants, and even more enhancement was observed, which we believe is because of the combined effect of enhanced thermal transport and also more site areas for the dispersion of these catalysts. Practical propulsion systems all operate at high pressures. For example, the most powerful liquid rocket, the RD-170 families, developed by Soviet Union in the 60s and 70s, the combustion chamber pressure is around 245 bar. So at that kind of pressure, ideal gas law is no longer valid because the molecules are very much packed. The interaction, the forces between the molecules are non-negligible. So it's challenging to model such processes because of the non-equilibrium nature and then departure from ideal gas law and the lack of interface between the gas and liquid. So we have been using molecular dynamic simulations as a tool to study the thermodynamics of supercritical fuels at high pressures. And the advantage of molecular simulation is that except a potential model that describes the forces between particles, and there are no other assumptions. For example, we don't need an equation of state, we don't need models of thermodynamic transport properties of the fluids. So with molecular simulations, we have been studying the thermodynamics and transport property of hydrocarbon fuels at high pressures. For example, the liquid-gas interface, which is on a nanometer scale, as well as the transition from the classical two-phase evaporation to the one-phase diffusion-dominated mixing regime. Molecular dynamics is a deterministic technique which studies the temporal evolution of the coordinates and the momenta of a set of interacting particles via the solution of Newton's second law of motion. So basically, each time step, the forces acting on the atoms are calculated and combined with the current position and velocities to generate new positions and new velocities at the next time step. So in this way, the MD simulations are able to capture the dynamics of a system. The thermodynamic averages are obtained from molecular dynamics as time averages. Understanding and control of ignition is critical to the performance of combustion engines, such as reduce emissions, improve efficiency. My group has been studying the fundamental mechanisms of ignition for various ignition technologies. For example, spark ignition, pre-chamber jet ignition, and plasma-assisted ignition. Now, among these technologies, pre-chamber jet ignition is widely used for large-bore natural gas engines, as well as F1 racing cars. This technology is currently being considered for gasoline engines for passenger cars as a replacement for traditional spark ignition. Now, the idea is to burn a small amount of fuel-air mixture in a small volume called pre-chamber. As a result of ignition combustion of the mixture in the pre-chamber, and multiple jets will be issued from the pre-chamber, these hot turbulent jets penetrates into the main chamber, cause ignition. Now, the advantage of pre-chamber jet ignition in comparison to traditional spark ignition is that ignition takes place on the surface of the jet in multiple places, which can potentially enable us to burn linear mixtures for combustion engines, as well as improve efficiency and reduce engine cycle variations. I'm standing inside one of the test cells at Zucrow Laboratory. We have unique facilities for energy and propulsion research. What's worth mentioning is the natural gas-fired air heater system, which is capable to deliver air at temperature up to 900 Kelvin, a pressure up to 40 bar, and a flow rate up to 0.25 kilogram per second. So we have been using this heated air system to study ignition phenomena at engine-relevant conditions without actually running an engine, which could be very complex and expensive. This is a GM 4-cylinder 2-liter gasoline engine. We have modified it to include optical axis and instrumentation. So with the heated air and this experiment, we have been examining the ignition mechanisms of pre-chamber, and this will help us, especially our industry collaborators, to design more efficient pre-chambers for gasoline engines. We have also utilized the high-pressure, high-temperature air facility to study spark ignition for internal combustion engines. One of the main issues for spark ignition is erosion of the electrodes, which is due to the interaction between plasma species and electrode material. So we have used the high temperature, high pressure air at various flow rate and running for hours. We have been able to study the erosion mechanisms of the different electrode materials.